Hello YouTube. In this video we're going to be discussing solving rational function inequalities, and this is kind of a build on to the last few videos that I made on solving polynomial inequalities, but something we're very familiar with in algebra is solving linear inequalities. We've just been moving on and extending this concept to higher degree polynomial inequalities, and so we'll extend this also to rational functions, because rational functions, let's face it, are just a polynomial divided by another polynomial. So let me scroll down a little bit here. Let us say we had a rational function. I think I've got one in particular that I wanted to use here. 2x minus 7. I'll write this down here. 2x minus 7 is our numerator polynomial, and on the bottom here we'll go with x minus 5, and I wanted to call this less than or equal to 3. Okay, so we're going to go ahead and get started with the same processes that we've used last time. It's just that when we find our critical numbers by first getting a 0 on the right, which by the way would be something we work through. I use this example specifically because a lot of people give problems where there's already a 0 on the right with rational functions. This one has a 3, so we're going to have to find a common denominator when we kick this back over here. But the bottom line is this. When we find critical numbers of this, we're going to find the zeros not only of the top but of the bottom as well. And we'll take a look at the graph and what this would mean if we interpret it graphically. So let's go ahead and start by subtracting 3 from both sides here, and we'll just get the algebra part of this out of the way. This is, right now, no part of this is like graph theory. This is just simply, you guys need to know how to do algebra. So 2x minus 7, x minus 5, minus 3, less than or equal to 0. Now that we have a 0 on the right, I'd like to find the zeros of this, but first of all, I'm going to need to actually absorb this quantity minus 3 or minus 3 over 1 into this quantity over here. So you might say, okay, so what's our common denominator? The common denominator between 1 and x minus 5 is the product of those two things. So essentially, we could take this over here times 1 times 1. Of course, that doesn't change anything about that ratio, but we say over here, we need to take this times x minus 5 on top and on bottom. So x minus 5. And I'm sorry about the sloppiness there, but we're going to rewrite this. So here's what we have. We have 2x minus 7 over x minus 5 that we had to begin with. And this is now minus 3 times x minus 5 on top over 1 times x minus 5 on bottom, which is just x minus 5. And you'll notice now that we have a common denominator between both of these quantities. So I would like to actually add these together. So we'll just say add the opposite. And of course, we could just interpret this as being a negative 3. But we can go and distribute this. So now everything is over this denominator, x minus 5. That's our common denominator. And on top we had on the left there 2x minus 7, and then we had negative 3 times x is negative 3x. Negative 3 times negative 5 is positive 15. So now combining like terms, here's what we end up with. We have 2x and negative 3x is negative x. Negative 7 positive 15 is positive 8. And we have x minus 5. Now keep in mind, this right here was just the expression on the left-hand side of our original, take a look right here, original inequality. So we were saying all of this stuff on the left was less than or equal to 0. So now I'm going to put that less than or equal to 0 back in here. We say, okay, well, some problems you'd probably start off with this right here, but basically we're saying, okay, we'd like to find the x values that would cause this to be true. I do want to say, one thing right off the bat. We can interpret this thing on the left as being some polynomial function, some rational function, f of x. That's sloppy. F of x. And so what we're really saying here is we're looking for all of the x values that would cause our function on the left here to be either less than or equal to 0. In other words, they would cause all of our y values to be less than or equal to 0. So one way to do this would be we could hop over to GeoGebra here. And actually I've graphed this already. You can see up here on the left, negative x plus 8 over x minus 5. And you might notice some things about this, starting with, well, I'll graph this line here, x equals 5. And we can change the properties of that line. Object properties, we'll make it dashed. So you can see a little bit better here. But we have a vertical asymptote at the 0 of our denominator here, of course. So we say it's undefined at x equals 5. And then, the one real 0 we have of this function is at positive 8. It actually crosses the x-axis at 8. We could find that by, of course, setting the numerator equal to 0 and solving it. But the question was this. We say, all right, look at Photoshop here. We say, what are all the x values, which is what we're solving for in a minute algebraically. But graphically, we're saying, what are all the x values that when you plug them in, you actually get y values that are less than 0 or equal to 0. In other words, we're really, graphically saying, what are all the x values that when I plug them in, my graph is either below the x-axis, negative y values, or actually right on the x-axis. So the important thing to note here is this. We could actually highlight these things. We say, what are all the x values, of course, that would cause my graph to be less than 0? it'd be all of these ones here. And if I highlight this there, all of those there, essentially less than or equal to 0, because you'll notice in the unshaded interval there, those are all positive y values. We're interested in this instance, and all of those that would cause it to be less than 0, or, like for example, right at 8, it would be equal to a height of 0. So the question is how we do this algebraically. All right, well, the first thing we need to do is this. If you need to write yourself a note, not only are we going to find the zeros of this here, we say zeros, we're going to find the zeros of the numerator polynomial and the denominator polynomial. And I'll just label those numerator of x and denominator of x. But so we're going to go ahead and start with that. If we said negative x plus 8 equals 0, then we get negative x is negative 8, and we get x is 8. So this right here, we want to label this. This is one of our critical values, critical vowels. All right? Groovy, baby. Here we go. So we say also, if you set that now the denominator equal to 0, this is going to be where our asymptote is, of course. We say, all right, well then x minus 5 is nada, so x is 5. And this is our other critical value. So we have two critical values here. And just like when you solve a polynomial inequality, what this does is it sets up our test intervals on our x-axis. So really we say, okay, well in this case, we've got our two critical numbers. Oh, I'm just going to make this 0 here. We say 1, 2, 3, 4, 5, 1, 2, 3, 4, 10, 10, 5. So we say critical numbers, critical values. I'm going to put x on those because I don't know if it actually includes those x values or not. But in this instance, it's a little bit different than the ones we've done in the past. I do want you to notice this is not just less than 0, it's also less than or equal to 0. So again, looking at the graph, it's actually at a height of 0 at 8. So 8, you know, when we test that, is actually going to be included in our solution set, whereas 5 here, it's not actually at a height of 0 at 5. So it's not going to include that critical number when we do this. So now we've got our test intervals. We can write this. We say intervals. Intervals for which we need to plug in a point and test the points. Okay, so we say, well, from negative infinity up to 5, that was one interval, up to that critical value. From that critical value up to the next critical value, from 5 to 8, label that here. And from 8 out to positive infinity. And of course, we already know by looking at the graph, well, all the x values that cause this to be negative or less, you know, y values to be less than 0 or equal to 0 are shaded here. So when we test these, it's not going to be a shocker, but let's take a look. So from negative infinity up to 5, we just need to pick an arbitrary x value from there to there. You know, we can hop over like a green or something like that. So I would, maybe I would test 4, I could test 3. Really conveniently though, we could test 0. So I say, all right, well, our original polynomial said this. We said negative x plus 8 over x minus 5 less than or equal to 0. If we plugged in 0, these two terms would drop out, and I get a positive 8 over a negative 5. Bottom line, I get a negative number, okay, and a negative number, negative value, is less than or equal to 0. So what this means is, of course, that if 0 works, then everything in this interval over here works. Let's go back to that greenish color. We say everything over here works. Everything over here works. So we need to ask this question this time. So would I include 5 or would I not include 5? That is, am I going to put an open parenthesis here or should I put brackets here? And the thing here is this. Again, looking at the graph, there's an asymptote at x equals 5. And so we say the y values are not actually equal to 0 there. I mean, they are less than 0, but we say, what if we plugged in 5? Okay, I'm going to plug in 5. So we plug in 5 into my function, I get negative blank plus 8 less than or equal to 0, and this is over blank minus 5. If I plug in 5, what I want you to notice is this. You do absolutely get like a positive 3 on top, but on bottom you get 0. And the main issue with this is it's just undefined. So when we write our test interval there, and we say that, well, the interval that works, we say, okay, we're going to put an open parenthesis on this one. Okay, so we say, and up here, if I was going to draw this graphically, I'd say, all right, this interval does not include 5. It's everything up to 5, but not including it. All right, well, let's pick another test value. We say, well, between 5 and 8, 6 would be a really convenient value to choose. So let's test between 5 and 8 here. We're going to know, you know, already this doesn't work by looking at the graph, but we say, all right, this would be negative blank plus 8 blank minus 5 less than or equal to 0. We're testing 6. We say 6 on top. We get positive 2. I just care that it's positive. That's all I care about. On bottom, I get positive 1. The bottom line is I get a positive divided by a positive is a positive value. I don't care what it is, even though it comes out to be positive 2. It does. And that's totally not less than or equal to 0. So what this means is if 6 fails, then everything on that interval between 5 and 8 also fails. So we say this interval is not included in the solution set. And of course, you know, looking at the picture, those were the positive y values. That's why it wasn't included here. Okay, last interval we need to test is a number between 8 and positive infinity. We could go for possibly, we'll go for 9 here. I'm just testing 9. So now we'll go back down here. We'll put these in our blanks. We say 9, 9. Check this out. On top we get a -1. On bottom we get positive 4. So what's a negative divided by a positive? Well, of course that's a negative. Of course we get -1/4 to be technical about it. But the point is we get a negative value and that's all we care about. And a negative value is less than or equal to 0. And so up here we would shade in everything from 8 out to positive infinity. We say, so this works here. It's just that this notation is actually wrong. At 8, we should actually test 8 this time. How am I supposed to know that? You know, well, here's the deal. It was less than or equal to. And whenever you have like an or equal to symbol, you should actually test your actual critical values. So what if we did indeed plug in 8 itself? Of course you know that 8 was a 0 of this function. So when we plug it in, you get negative blank. You know, so -8, plus 8 over 8 minus 5 less than or equal to 0. Sorry about squeezing that in there, but basically you get 0 over, we don't care as long as it's not 0, but and this is true. 0 is less than or equal to 0. So keep your eyes open for something that says less than or equal to or greater than or equal to. You actually want to test your critical values. So what this means is this interval here, when we write the answer, we're going to fix this. It has a closed bracket on there because it includes 8. And the same thing up here on the picture. We would say graphically it would look like this. Graphically look like that. And again, just to reiterate that, it's because it's actually at a height of 0. The y values are at a height of 0 for that x value. So cheers.